the common gate configuration, in which your gate, you see in this configuration, this is for the biasing of the circuit in figure 32. So the gate is at the signal ground, okay, and this is being ensured by the bypass capacitance CG. Okay, so the gate is the AC ground. The resistance RG that you're looking at over here is there just to prevent any static charge buildup at the gate terminal. Okay, and you also notice that the input signal is now being applied at the source terminal. Okay, which is also being biased by the constant current source IQ. And then at the drain, you are taking the output. Okay, the output is being coupled by the coupling capacitor CC2. Okay, CC1 is coupling the input, while CC2 is coupling the output at the drain. Okay, RL is the load resistance, right? So then again, you see, in order to evaluate the important small signal voltage and current gains, you have to consider the small signal equivalent circuit as we have done before. So this is small signal equivalent circuit of the common gate amplifier. So once again, we ignore all the capacitive reactances for CC1, CC2, and CG. So ignoring all these capacitive reactances, we have this input Vi. Then the formation of this source is a Thevenin voltage and output having an output equivalent source resistance RSI. Okay, it's not a Norton configuration, it's Thevenin. So RSI is the output source resistance over here. So then you see CC is an AC short circuit, so the gate comes at the ground. The gate is at the ground terminal. This is your gate. So the direction of the current, if you notice over here, it's out of the source. Okay, so it's coming out of the source and then it's into the drain. So from the drain, it's going out of the source. So the direction is as such. Okay, so for the transconductance amplification, you have this GM VGS. VGS is the input AC voltage. Okay, note the sign of VGS over here. So this gate is at more positive potential with respect to the source for this NMOS configuration. So your current II, which you see over here in this direction, II is negative of minus GM VGS. Okay, so II is minus GM VGS. Okay. Also, you note that the R naught we have taken is there is no R naught, the output resistance, small signal output resistance of the transistor. Okay, so we are assuming R naught to be infinite. Okay, R naught is infinite. So this is the case when the channel width modulation parameter lambda is 0. Okay, then at the drain terminal you are taking the output V naught. Okay, this is your source terminal. This is your gate terminal, and at the drain you are taking the output V naught. CC2 is again short circuited, so it's very easy to construct. So between these three terminals of the transistor, source, gate, and drain, gate is at ground. Okay, from the drain you take the output, you short the CC2 coupling capacitor, and you kill all the DC sources. So V positive is again 0 over here. So it becomes a parallel combination of RDRL at V naught at the output voltage terminal, which is the drain terminal. Okay, then R naught is taken as infinity, so it's open circuit. We don't need to consider that. Okay, otherwise it would have appeared like this, R naught. So we are between the drain and source. We are not considering R naught over here. So between drain and source, the direction of the current given an NMOS device is as such, which is shown in the dependent current source. This is GMVGS. Okay, gate is at ground, and then at the source you have the input. Okay, so that completes the small signal equivalent circuit of the common gate amplifier. Okay, now, okay, so the comments are written over here. So you see in the common gate configuration, the input signal is applied to the source terminal, and the gate is at the signal ground. Well, if you recall, in the common source and in the source follower configurations, we were applying the input at the gate terminal. Okay, but over here in this configuration, the only difference is that the input is at the source. Okay, and you will see that most of the time this configuration is useful for providing current gains. Okay, so In this configuration, the input signal is not the voltage signal. Usually, it's the current signal. Okay, so you can replace this part of the source by the equivalent Norton equivalent circuit. Okay, you can have a current source followed by a parallel Norton equivalent resistance, right? So you can convert these Thevenin equivalent source model by a Norton equivalent current model. Okay, so the input is the current, and the output is again an amplified current. Also, you will note over here that the input resistance Ri is small, so this is also useful. It's an advantage as far as the current amplification is concerned, because if the input resistance is small, the it's going to provide a better current amplification. Okay, there won't be any loss or drop of the voltage at the input. Okay, then the common gate configuration shown in figure 32 is biased with a constant current source IQ, which you see over here. Okay, so IQ is the current biasing source. The gate resistor RG prevents any buildup of the static charge on the gate terminal, and the capacitor CG ensures that the gate is at a signal AC ground. Okay, this CG ensures that this is a short circuit at AC, so the gate is at ground, which you see over here. Then the coupling capacitor CC1 is coupling the signal to the source. Okay, CC1 is coupling the signal to the source, while the coupling capacitor CC2 couples the output voltage to the load resistance RL. Right now, so in this small signal model, small signal transistor resistance R0 was assumed to be infinite. We have ignored this resistance. Okay, otherwise there would have been a resistance R0 between source and drain terminal like this. So we have ignored this. So R0 is infinitely large. Okay, so we don't need to bother about it. This is an open circuit, and this happens when in this model once you have the channel width modulation parameter as 0. So you can assume channel width modulation parameter as 0, which means that for the channel resistance in NMOS device, there is no dependence of the channel resistance on PDS. Okay, which is responsible for the horizontal electric field, which drives the charges from source to drain. So the resistance, or you can say in IV characteristics, the IV characteristics are pretty much the ideal case. Okay, so in saturation, the current has a flat or a plateau type region characteristics. There is no rising characteristics like this. So lambda is 0. Okay. All right. Now, if you look at this configuration, you see V0 is given by minus GMVGS, given the current direction, minus GMVGS into the parallel combination of RD/RL. This is the same node. Okay, this is the same node of drain. This is the drain node. So RD can be combined with RL in a parallel fashion over here. And then given that the current direction, you just multiply this with minus GMVGS. This gives you the output voltage, the AC output voltage. Then writing the KVL equation around the input. This is the input loop. All right. If you write the KVL over here, well, you have there's a certain voltage drop at the output source resistance. So this is I RSI minus VGS. Okay, so this is equal to VI. So basically, the input voltage that is being applied by the source is bifurcated into two drops. One happens at the source resistance RSI, and the other drop is at VGS. Okay. So also note that this II current, the input current, is minus GMVGS. It is minus GMVGS. So because there's no current into the gate of the device, okay, so these two currents are in the opposite direction. So according to KCL, if you apply KCL at this node at source, then you can write this as II plus GM. At the source node, this can be written as II GM VGS, okay, which is my current. The MOSFET current is equal to 0, okay, because there is no gate current, okay, because of the infinite resistance at the gate terminal. So II is minus GM VGS. Now, if you substitute this over here in the KVL equation, so you can express VGS in terms of VI like this. Okay. So if you do some algebraic manipulation, you will find this that VGS is minus VI over 1 plus GM RSI. Okay, so basically over here this VI becomes minus GM VGS RSI minus VGS. So you can make VGS as the subject of the formulation, and you can express this in terms of the input signal. Right now, in the output voltage relation, if you substitute back your VGS, the definition of VGS in terms of VI, you can derive the voltage gain of the small signal model AV as V naught by VI. So this is V naught by VI, and you can see this that you have in the in the numerator you have minus GM RD RL. Okay, VI goes in the denominator to make it as a voltage gain. Then this denominator is the same that comes over here. Okay, this is my voltage gain for the small signal model. So this voltage gain also, you note over here, is positive. That means the output and the input signals are in phase. So if you recall, for the common source configuration, AV was negative, which means the input and output voltages were 180 degree out of phase. Okay, which is not the case in the common gate configuration, and also in the common drain or source follower configurations, you don't have this AV negative. Okay. All right. Now, in many cases, the signal input, as I've mentioned earlier, to a common gate circuit is a current. So we are looking for the current gain. Okay. So what is different is that what we've done is we have replaced this part by the Norton equivalent current circuit. So this source part will consist of a current source instead of voltage source, and there's an equivalence between this Norton configuration and the Thevenin configuration, having both sources sensitively represented by RSI, but this is connected in parallel with the current source, so you can derive the equivalence between II and VI over here in terms of RSI. So in this configuration, we have replaced this by a Norton circuit. Okay. Then again, VGS is shown by infinite. The gate has an infinite resistance. Okay, so the same polarity of VGS is shown as we had previously over here. Rest of the circuit is pretty much the same. Okay, rest of the circuit we have minus GM VGS. This is your drain terminal. Okay, this is your source terminal. The gate is at ground. The gate is at ground. Just the source has been replaced by the Norton equivalent. Okay, so figure 34 shows the small signal equivalent common gate circuit with the Norton equivalent circuit as the signal source. The signal source is replaced by the Norton equivalent. That's it. And remember, this Norton equivalent and the Thevenin equivalent is one and the same thing. Okay, you can derive the equivalence between VI and RSI over here, VI and II over here. II is the input current. Notice over here, II over here, this is the input current. This II becomes the independent current source. So okay, now we can calculate a current gain. The output current I naught can be written as, now I naught is the current in the load branch. So you can write this the drain. So just at the drain we were taking V naught, if you recall. So if you recall that V naught is equal to the node voltage V naught is equal to minus GM VGS minus GM VGS. It's a parallel combination of RD and RL. Okay, so this is basically, I can write this as RD into RL divided by RD plus RL. Okay. In order to consider the current in just the load branch, what we can do is, you see, IL or I naught in this case is your V naught by RL. This is V naught by RL. Therefore, what we are left with is minus GM VGS. That's my output current. Okay, so I'm interested in how the output current relates to the input current. Therefore, we can have a current gain of the common gate configurations. So this is RD over RD plus RL. RD plus RL. So you see this expression is what we have. This expression is what we have over here. Okay, minus GMVGS into RD plus RL in the denominator. Okay, this is the output current. Now at the input, what is happening is we have this current source II. So this current source is there at this the source terminal. It's coming into the source, and then coming to the source is another transistor current. One is from the source, and the other is a transistor current, GM-VGS. And since there is no current in the terminal, the gate terminal, so we can write this as II plus GM-VGS plus, well, for the Norton equivalent, we are going to have a current in this branch. Okay, no current at the gate branch. We're going to have a current in this branch. So this is equal to VGS, which is across the source and gate terminals. So due to the polarity of this comes with a plus over here. This is VGS over RSI is equal to 0. Okay, and then you can express this VGS in terms of the input current. You can take VGS common, and then you can express this in terms of the input current over here. And if you substitute this VGS for VGS in this expression, you can bring the input current II, okay, out, and this II can, if you substitute this in the output current equation, you can form the small signal current gain AI, which is I naught over II, and that can be expressed in terms of the resistances RD and RD plus RL. Then you have this factor, this which is also a form of voltage divider, not exactly voltage divider, but I mean this comes with the it's coming from the VGS expression, the same expression you're going to have over here. Okay, so GM is going to multiply with the RSI. Okay, so you're going to have a factor over here, GM RSI. Then the denominator is the same. Okay, so this is your current gain basically. And now if you should look closely at this expression, you may note that if your drain resistor is much greater than the load resistance, first of all, and secondly, your product of transconductance gain and RSI, if that is greater than 1, then that means that the current gain is essentially a unit. Okay, it's a unity. So that becomes your that means your output current I naught is basically following the input current. Okay, it becomes a current follower circuit. So under these two conditions, if RD is much greater than RL and GM RSI is much greater than 1, then the output current is basically equal to the input current. Okay. Okay, now what we are left with is we have derived the voltage gain and the current gain. We saw that the voltage gain was positive, it's greater than unity, and we have seen that the current gain is given by this expression over here, okay, between the output and input current. And what we left is with is the input and output impedance. So in contrast to the common source and source follower amplifiers, the common gate circuit has a low resistance because of the transistor. So however, if the input signal is a current, the low input resistance is an advantage. So the input resistance is defined using figure 33. So over here, if you bring back that Thevenin equivalent circuit of the source, II, in terms of II, RSI, VI, you can write this RI as since the since at the source terminal over here, at the source terminal, the voltage is minus plus, given the polarity, it's VGS. Okay, so RI is given by VGS minus VGS over II. Okay, and you notice that since there is no current into the gate of the transistor, II, the input current, is minus GMVGS. It's minus GMVGS. So if you substitute this over here in the denominator of the input resistance, II, you get the RI as 1 over GM. And if you note that GM is the transconductance parameter of the transistor, having units of amps per volts. Okay, So this becomes volts per amps. So that is resistance. So the resistance is usually small. It's 1/GM, and GM is not a um, very large quantity. So in practice, you will have at most the input resistance will be limited by a few hundred ohms. Okay, so the input resistance is low for the common gate configuration, and predominantly or only it's only being affected by the transconductance gain of the transistor. It depends on the transconductance gain of the transistor GN. Then if you want to find the output resistance, you can set the input signal voltage first to 0. So you have to kill this source over here. Okay, and from figure 33 we see if you do that, then well, VGS becomes equals to minus GM VGS because of this current, because we were taking the um, we are taking II as minus GM VGS. Okay, because I minus GM VGS, so it's minus GM VGS flowing into RSI. So minus GM VGS RSI has to be equal to VGS. Well, what does this mean? This implies that VGS should be 0. Okay, so this equation is satisfied only with VGS is 0. So when VGS is 0, just forget about this part, and the output resistance looking um, from the load side, if you look into the transistor, it's only the drain resistance you're left with. That means the output resistance is the drain resistance. Okay, so which could be respectable. So the output resistance is not small, which means that the loading effect would be there for the common gate configuration if you are going to integrate more electronics or more load at the output. Okay, there will be loading effect because of the finite RD. All right, so consequently, if you kill the input source Vi, then GM-VGS is equal to 0. The output resistance, looking back from the load resistance, is therefore R naught is equal to RD. Okay, so this is also gone, and you are left with the output resistance is RD only. Okay, the output resistance is RD, whereas the input resistance is 1/GM, which is small. Okay, and it's better for the current amplification purposes. Now, there's an example 4.10 from the course text, and the objective is that for the common gate circuit, determine the output voltage for the given input current. So we have to determine the output voltage for the input current, and we are going to use the same circuit, Norton equivalent circuit, for the AC equivalent circuit and the small signal model of the transistor. This is your common gate circuit, figure 32, that we have seen in initially for the common gate configurations. So for the circuit shown in figure 32, 34, the circuit parameters are, we're given the quiescent current, which is the saturation current, as 1 milliamps for the common gate amplifier, and then you're given the biasing, the biasings V plus V negative plus minus 5 volts. RG at the gate is given as 100 Ks. RD is the drain resistance. RL is the load resistance. The values are given 4 Ks and 10 K respectively. The transistor parameter, the threshold voltage is 1 volt. It's an NMOS device, so it's positive. Then the conduction parameter is 1 milliamps per volt square. So since we are not considering any R naught, that means lambda, the channel width modulation parameter, is 0. Okay, so basically your output transistor resistance is an open circuit. So assume the input current in figure 34 is 100 sine omega t microamps, and RSI is 50K. So RSI is given as 50K. II is given as 100 sine omega t. Now the quiescent gate to source voltage can be determined from the saturation relationship of the current and VGSQ. Okay, so we have VTN. Okay, we have the conduction parameter, we have IDQ. So the only unknown is VGSQ, which can be found from this relation as 2 volts. Okay, now from this information we can find the transconductance gain as 2Kn VGSQ minus VTN. Now we have Kn as 1, it's 1 milliamps per volt square. VGSQ is known as 2 volts, VTN is 1 volt, so you find GM as 2 milliamps per volt. Okay, but you can also find GM in terms of the drain current directly. I mean, you don't even need VGSQ for that, but it's one and the same thing. I mean, you can do it like this also. So this is also twice under root of IDQ into Kn. Okay, same thing. Result is the same. Multiply by Kn. And you notice that Kn and IDQ both are unit. So IQ is 1 milliamps. Kn over here is 1 milliamps. Okay, so it's become 1 milli squared. So this basically becomes, so in the square root this becomes 2. This becomes 1 milliamp again. So this becomes 2 milliamps per volts. The result is the same. I mean, you can use any expression to evaluation of the transconductance gain of the transistor. Okay, so we have the transconductance gain. R0 is infinity. So let's not bother about that. What are we left with is the current gain. Now, this expression over here, we have derived this before, if you recall over here. Let's use the same expression for the current gain. And this expression was based on whatever is your output current in the load branch RL. So we considered the output current in the load branch. Then we brought the input current by considering the applying the KCL at the input. So just I mean, from here you can express VGS in terms of II and then substitute it over here. Then that brings your input current against the output current, and you can have the voltage, the current gain in the relationship. Okay, let's use this because we have the values of. Now we know that what is RD, what is RL. Okay, so we know all these quantities. We know GM is 2 milliamps per volts. Okay, RSI was given as is given in the question as 50K. So everything is known. Okay, so all we need to do is just plug the values of RD, RL, RSI, and the transconductance gain GM. So if you do so, you'll find out this RD, RL. This is 40 divided by 14, and then you have this GM is if you do this, you can find the current gain. This relationship is only going to give you the current gain AI as I0 by II. Okay, so this relationship is only going to give you the current gain. For the output voltage V0, V0 is given by I0 RL. So that means you have to multiply this relationship with RL. That just brings RL in this expression. Okay, so from here to here, there is only difference of RL. There is only one difference, and that's RL. And II is given as 0.1 sine omega t. Just substitute the values for GM, RSI, RD, RL, and you find that V0 is equal to 0.283 sine omega t. Volts in volts. Okay, this is volts. So the MOSFET common gate amplifier is useful if the input signal is current. Okay. Also, if you note over here, what is your input resistance? So input resistance is 1 over GM, which is how much? Which is 1 over 2 milliamps, 2 milliamps per volt. So that is half into 1000 because of milli. Okay, so you have this about 500 ohms. This is the input resistance is about 500 ohms, and the output resistance is dependent on RD only. So the output resistance R0 is basically RD, which is given as 4 kilo ohms. So that is 4 kilo ohms. So that is your input resistance, and then the output resistance. Okay, the input resistance is 0.5 kilos, which is small. The output resistance is dictated by the RD. Okay, we are not considering R0 in this configuration. So that completes the evaluation for this question. Okay, so we were required to evaluate the voltage. Okay, so we were required to determine the output voltage, which we have done for the given input current. So you note that mostly in this configuration, the input current, the input resistance is low, and the device is used when the input source is the driving source is the current source. Okay, and the output is the current again. So it provides some current gain over here, right? So that's all for this example.